Every planet in our solar system is shaped by the same basic rule. Gravity pulls matter inward until a world becomes roughly spherical. Then there is Haumea. It is not a sphere, it is shaped more like a rugby ball, stretched and flattened as it spins through the darkness of the outer solar system. Haumea completes one rotation in just 3.9 hours, faster than any large object in the solar system. That rotation is so extreme that it has permanently distorted the entire world. Haumea stretches roughly 1,960 kilometers, about 1,218 miles, along its longest axis, but only about 996 kilometers, roughly 619 miles, along its shortest, and that is only the beginning. Haumea has two moons, and both may be made from material blasted off Haumea itself. It also has a thin, dark ring, discovered when telescopes on Earth watched a distant star briefly disappear behind the dwarf planet. Something enormous must have happened here. The leading explanation is a collision billions of years ago, violent enough to strip away much of Haumea's outer ice and send fragments into orbit. Those fragments may have become its moons, its ring, and an entire family of icy objects scattered through the Kuiper Belt. There is even a strange dark red region on its surface whose composition remains uncertain. And then there is the discovery itself. The scientists involved became locked in a dispute over who found Haumea first, turning one of the outer solar system's strangest worlds into the center of a scientific and naming controversy. So Haumea is not simply a dwarf planet that happens to look unusual. Its shape, its speed, its moons, its ring, and its scattered family of fragments may all be evidence of one ancient catastrophe. A world was hit, it was broken apart, and somehow the pieces kept moving together. A like, a subscribe, whatever feels right. It all helps this channel reach more people who love falling asleep to the sound of the universe. The story begins with the collision that changed Haumea forever. Beyond Neptune, the solar system does not simply end, its architecture changes. The Kuiper Belt begins where the giant planet Neptune gives way to a broad, flattened region of frozen debris. Its inner edge lies around 2.8 billion miles from the Sun, while its outer reaches extend to roughly 4.6 billion miles. From our perspective, this region can seem almost empty. In reality, it contains an enormous population of ancient bodies. Hundreds of thousands of objects larger than 60 miles across may occupy this distant reservoir, along with countless smaller fragments. They are leftovers from the material that surrounded the young sun about 4.5 billion years ago, preserved far from the warmth and activity of the inner planets. The scale becomes easier to appreciate beside the asteroid belt. That familiar band between Mars and Jupiter is much narrower. The Kuiper Belt stretches roughly 20 times farther across, and its total mass may reach 200 times that of the asteroid belt. We are looking at a vast archaeological layer of the solar system spread across billions of miles. Haumea occupies this frozen territory at an average distance of about 4 billion miles from the Sun. At that distance, sunlight is already faint, and the seasons unfold on timescales far beyond a human lifetime. One complete journey around the Sun takes Haumea approximately 285 Earth years. For most of human history, no one knew this world existed. The first observations associated with its discovery came from a team led by astronomer Mike Brown at the California Institute of Technology using the Palomar Observatory. The object was later recognized as a new member of the distant population beyond Neptune, becoming part of the growing evidence that the outer solar system contained far more worlds than astronomers had once imagined. In 2008, The International Astronomical Union formally recognized Haumea as a dwarf planet, following Pluto, Eris, and Ceres. The classification has a precise meaning. A dwarf planet orbits the Sun and has enough mass for its own gravity to shape it toward equilibrium, yet it has not cleared the surrounding orbital region of comparable bodies. Haumea satisfies the orbital requirement and has enough mass to become a differentiated world, but its unusual shape makes the definition more interesting. Its gravity does control its overall structure, while its extraordinary rotation alters the form that equilibrium takes. So its place in the Kuiper Belt is more than an address. It is the setting in which Haumea's history becomes possible, surrounded by remnants of the same ancient material from which it formed. 4 billion years ago, somewhere within this distant population, another body crossed its path. The encounter would leave its mark across Haumea and throughout the space around it. Haumea's dimensions resist the instinct to picture a world as a globe. Measured across its three principal axes, it stretches about 1,218 miles at its longest, 775 miles across its middle, and only 619 miles along its shortest axis. That geometry has a name, a triaxial ellipsoid, meaning a body whose three axes have different lengths. Imagine an egg stretched in one direction and compressed in another. Haumea takes that form to an extraordinary degree, with its longest axis exceeding its shortest by roughly 599 miles. For a body this large, such an arrangement should immediately raise a physical question. Gravity pulls matter toward the center from every direction, tending to erase major irregularities. When a world becomes massive enough, its own gravity can overcome the strength of its rock and ice and reshape the body into its lowest energy configuration. This condition is called hydrostatic equilibrium. In a slowly rotating world, that equilibrium is very close to a sphere. Haumea reaches equilibrium differently. Rotation changes the balance. At Haumea's equator, the surface travels at approximately 2,887 miles per hour. That speed creates a centrifugal effect, an apparent outward force associated with rotation, strongest around the equator. Material there is continually urged away from the axis of rotation, while gravity pulls it inward. The result is a remarkable compromise between competing effects. Haumea's equatorial region swells outward, while the polar regions become compressed toward the center. The difference is immense. Its shortest dimension is roughly 300 miles less than its longest, giving the dwarf planet its unmistakable elongated profile. You can think of the shape as a record of motion frozen into the body itself. Every rotation contributes to the balance, and every layer of Haumea responds according to the same physical rules. The rock beneath the surface, the water ice above it, and the gravitational field surrounding the world all participate in a single rotating structure. There is another consequence hidden in those dimensions. Haumea's shape is not merely an unusual appearance observed from Earth. It tells us something measurable about the forces operating throughout the entire body, allowing astronomers to test models of its mass, density, internal structure, and rotational state. The mathematics becomes especially revealing near the limits of stability. Increase the rotation of a body far enough, and centrifugal effects can eventually overpower gravity at the equator, allowing material to escape. Haumea spins rapidly enough that its present form lies close to this extreme regime, yet the world remains intact. Its elongated body has persisted for billions of years, held together by gravity, while rotation continuously reshapes its equilibrium. Seen this way, Haumea's strange outline is a physical signature rather than a surface oddity. The dimensions preserve the memory of an immense rotational impulse, written directly into the geometry of a world that has carried that motion across deep time. On Haumea, a full day passes before most of us would finish breakfast twice. One rotation takes only 3 hours and 54 minutes, an interval shorter than the working day of many clocks. Earth needs 24 hours for one turn. Mars takes about 24.6 hours, and even Jupiter, the fastest spinning planet, requires roughly 9.9 hours. Haumea moves through this cycle more than twice as quickly as Jupiter. During 8 hours of sleep, it turns more than twice, presenting different portions of its stretched body toward the distant sun and toward us. The speed is remarkable, yet the real discovery lies in how astronomers measured it without placing an instrument anywhere near the dwarf planet. They watched its brightness change. As Haumea rotates, its elongated shape changes the amount of sunlight reflected toward Earth. Its broader profile produces a brighter appearance, while the narrower orientation produces a dimmer one. These changes repeat with remarkable regularity, creating a light curve, a record of brightness variations that can reveal a rotating body's shape and spin. By timing those repeating fluctuations across many observations, astronomers determined Haumea's rotation period with exceptional precision. The measurement is especially valuable because the pattern is tied directly to the body's physical orientation, giving us a way to track its motion across billions of miles. There is something unusual about how stable that motion has remained. Over the timescales we can observe, Haumea shows no meaningful slowing of its rotation. Its present spin is thought to have persisted for roughly 4 billion years, surviving immense stretches of planetary history without losing enough angular momentum to alter its basic character. Yet the rotation cannot increase indefinitely. Every spinning world has a breakup limit, the point where outward rotational effects at the equator become strong enough to overcome gravity and release material. Haumea approaches this boundary unusually closely. Its equatorial surface moves at about 2,887 miles per hour, placing the outermost material in an extreme gravitational balance. Escape velocity is the minimum speed required for an object to leave a body's gravity without falling back. At Haumea's equator, that escape speed is remarkably close to the surface's rotational speed. A small disturbance to loose material could therefore make orbit a plausible destination. The distinction matters. Haumea is not merely rotating quickly for a distant dwarf planet. Its entire structure exists within a narrow physical regime where gravity and rotation continuously negotiate the body's survival. We can measure the rhythm from Earth, but the rhythm itself carries a much older signature. A spin this extreme requires an origin capable of supplying enormous angular momentum, and that points toward an event powerful enough to change Haumea's entire physical history. A collision in deep space can leave a signature that lasts for billions of years. Haumea carries one of those signatures in its rotation, composition, and surrounding debris. The leading explanation is a giant impact roughly 4 billion years ago, when the young outer solar system contained many large bodies crossing unstable paths. The impactor may have been hundreds of miles across. It struck Haumea at high relative speed, delivering an immense amount of energy in a single encounter. The geometry mattered enormously. Models favor a glancing collision rather than a direct impact, allowing Haumea to survive while receiving a tremendous transfer of rotational energy. That transfer is described through angular momentum, the quantity that measures how strongly a moving body tends to keep rotating. Angular momentum is conserved. Once Haumea acquired its extraordinary spin, there was no simple mechanism for making that motion disappear. The rotation could therefore persist across geological ages, while the collision itself became an ancient event preserved through physical evidence. Something else happened during the same encounter. The impact excavated material from Haumea's outer layers and launched ice-rich fragments into surrounding space. Some material remained gravitationally bound, some escaped entirely, and some gathered again under their own gravity. The surviving fragments formed a dispersed population around Haumea. Others eventually became larger companions, while additional debris may have contributed to the ring discovered much later. What looks like a collection of separate objects can therefore be understood as the aftermath of one enormous disturbance. The collision also altered Haumea's internal proportions. Its outer regions were richer in water ice and less dense than the rocky material beneath them. Removing substantial lighter material left the remaining body unusually rich in rock, helping explain its elevated density compared with many other objects in the Kuiper Belt. We can reconstruct this history because the evidence connects several independent observations. The rapid rotation fits an enormous transfer of angular momentum. The unusual density fits substantial loss of icy material. The moons contain crystalline water ice resembling Haumea's surface, while the surrounding family of icy objects shares related orbital and spectral properties. Each clue reaches back toward the same ancient moment. Imagine standing above that region 4 billion years ago, before planets had settled into the arrangement we recognize today. Two large icy bodies approach one another across the darkness. Their paths converge, their surfaces meet, and in an instant, the architecture of an entire system changes. The impactor disappears into the collision. Haumea survives, transformed. Around it, fragments begin following new trajectories, carrying pieces of the original body away from the impact. Over immense stretches of time, gravity sorts those fragments into different orbits and structures. What remains today is a physical record of that encounter, preserved in a rotating world and the material that still travels around it. Haumea's companions are therefore more than satellites in the usual sense. Their existence may represent surviving pieces of a body that was once part of Haumea itself. Two small worlds circle Haumea, carrying names from a very old Hawaiian story. Haiyaka and Namaka were daughters of the goddess Haumea, and in the mythology, both were born from their mother's body. Here, the connection between name and science feels unusually precise. Haiyaka is the larger of the two, measuring about 217 miles across. Its orbit carries it roughly 30,100 miles from Haumea, where it takes approximately 49 and a half Earth days to complete one revolution. Farther inward, Namaka is much smaller, measuring about 106 miles across. It travels around 15,000 miles from Haumea and completes an orbit every 18.3 Earth days. Their distances matter because the two moons do not move through space independently. They remain gravitationally bound to the same unusual parent, and each orbit carries information about how the entire system formed. The strongest clue comes from their surfaces. Both moons contain abundant crystalline water ice, closely resembling the material covering Haumea. Crystalline ice has an ordered molecular structure, and finding that same distinctive material on both satellites strongly supports a shared origin. Two unrelated objects captured by Haumea would be unlikely to reproduce such a close compositional match. Haiyaka's motion is comparatively orderly. Its orbit is close to circular, allowing the larger moon to follow a stable path around Haumea. Namaka behaves differently. Its orbit is more elongated and inclined, and its orientation gradually changes through a process called precession, meaning the direction of the orbital path slowly rotates through space. Haumea's shape plays a role in that motion. A spherical world produces a comparatively simple gravitational field, but Haumea's elongated structure distributes mass unevenly. Namaka, therefore, experiences subtle gravitational influences that would be absent around a perfectly round body. The two moons also influence one another. Their mutual gravity continually alters their orbital motion, creating a system in which small changes can accumulate over enormous spans of time. Astronomers have modeled these interactions to reconstruct how the satellites may have evolved since their formation. That makes the system more than a large body with two companions. It is a connected gravitational structure with the parent influencing both moons while the moons respond to each other. You can trace the evidence backward. The unusual ice points toward a common source. The orbital arrangements preserve clues about their evolution. Their gravitational interactions reveal that the system has continued changing since its formation, even though those changes unfold far too slowly for us to notice directly. Hayaka and Namaka therefore carry pieces of Haumea's history in two different ways. Their surfaces preserve material evidence, while their orbits preserve dynamical evidence. Both are remnants of an event that transformed their parent, leaving fragments behind that eventually became worlds of their own. They remain bound to Haumea today, still following paths shaped by the same gravity that holds the entire family together. A star can reveal a world without ever touching it. In January 2017, astronomers used that principle to uncover something circling Haumea that nobody had seen before. The event was a stellar occultation, when a solar system body passes between Earth and a distant star, briefly blocking its light. 12 telescope stations across Europe and Colombia prepared for the alignment, each watching the same star from a different location on Earth. The timing mattered enormously. Haumea's path and the star's position allowed astronomers to predict when the crossing should occur, while Earth's rotation determined which observatories would see the event. For a few moments, every telescope became part of one widely separated experiment. Then the star disappeared behind Haumea. That part was expected. Its light returned as the dwarf planet moved onward, restoring the star to view. But several stations recorded additional dips in brightness before Haumea reached the star, followed by matching dips after it had passed. Something was crossing the star twice. The symmetry was the clue. Material extending from both sides of Haumea could produce exactly this pattern, and the repeated signal appeared in observations from multiple locations. The simplest explanation was a ring surrounding the dwarf planet. Its dimensions were remarkable. The ring is roughly 43 miles wide and circles Haumea at a distance of about 1,430 miles from its center. Yet it had remained undetected for 13 years after Haumea itself became known. Part of the difficulty lies in its material. The ring appears to contain dark water ice, giving it far less reflectivity than the brilliant rings surrounding Saturn. From Earth, such particles can become almost lost against the faint light of the distant system. There is also an unusual relationship between the ring and Haumea's rotation. The particles occupy a 3-to-1 orbital resonance, meaning that for every one circuit completed by a ring particle, Haumea rotates 3 times. Resonance describes a repeating gravitational relationship that can help maintain material within a particular orbital region. The discovery made Haumea the first confirmed dwarf planet known to possess a ring. Only 2 smaller bodies, Chariklo and Chiron, were then known to have rings as well. We still cannot determine when Haumea's ring formed. It could be ancient debris left by the collision that reshaped the dwarf planet, or younger material continually replenished by impacts striking its surface. Either way, the ring transformed a distant point of light into a much more intricate system. A brief stellar disappearance had revealed material too faint to photograph directly, turning a few seconds of changing brightness into evidence for an entire structure orbiting far beyond Neptune. And the same observation did something else. By tracing exactly how the star vanished and returned at different locations on Earth, astronomers could measure Haumea's outline with a precision that earlier observations had never achieved. The 2017 occultation did more than reveal a ring. It changed the physical portrait astronomers had been carrying for years. Before that event, Haumea's dimensions were inferred indirectly from its brightness and estimated reflectivity, known as albedo. A brighter object can appear larger, but only if we know how much sunlight its surface reflects. Any uncertainty in that reflectivity passes into the estimated size. The occultation offered something much more direct. As Haumea crossed the distant star, each telescope recorded the exact moment the star disappeared and returned. Because the observatories were separated across Earth, their measurements traced different chords across Haumea's silhouette. Put those paths together, and we can reconstruct the body's three-dimensional outline. The result was larger than earlier estimates suggested. Haumea's longest axis measures about 1,218 miles, its middle axis about 775 miles, and its shortest axis about 619 miles. Those measurements matter beyond simple dimensions. They allow astronomers to calculate volume with far greater confidence, which can then be compared with Haumea's measured mass. From those two quantities comes its bulk density, a measure of how much matter is packed into a given volume. The result supports a body strongly dominated by rock beneath its icy exterior. It also gives researchers a firmer basis for comparing Haumea with other distant worlds, because size and mass can now be considered together with much less uncertainty. The occultation, therefore, strengthened the physical picture without requiring anyone to approach Haumea directly. It also offered another useful test. An atmosphere would have changed the way the background star disappeared. Instead of an abrupt loss of starlight, gases surrounding Haumea would have caused the star to fade gradually as its light passed through increasingly dense layers. That gradual fading was not observed. The stellar light dropped sharply, then returned sharply, placing strong limits on any atmosphere surrounding the dwarf planet. At Haumea's distance from the Sun, the result is physically understandable. Volatile substances that might form a substantial atmosphere would tend to freeze onto the surface or escape into space over immense periods. Still, the occultation could only reveal Haumea's outer boundary. It could not show mountains, fractures, valleys, or individual regions across the surface. Even the dark red area remains beyond the resolving power of these observations. We can measure the silhouette without seeing the landscape. That distinction is easy to miss. A precisely measured outline can tell us an enormous amount about a distant world, while leaving the actual terrain almost completely inaccessible. For Haumea, the occultation transformed uncertainty about its overall dimensions into a much firmer physical model, while preserving the deeper mystery of what lies across its surface. There is a place on Haumea where the surface appears different from almost everything around it. As the dwarf planet turns, this region alters the light we receive, leaving a subtle fingerprint in the changing brightness. Astronomers call it the dark red spot. It covers a substantial portion of one hemisphere and reflects light differently from the surrounding bright water ice. To identify that difference, scientists use spectroscopy, the process of separating reflected light into individual wavelengths so that materials can reveal their chemical signatures. The result has been intriguing. The spot is redder and darker, yet observations still detect crystalline water ice across the region. Something else appears to be mixed with it, changing the way the surface reflects sunlight without revealing its exact identity. One possibility involves tholins, complex organic materials produced when simple molecules are altered by energetic radiation over immense periods. Similar compounds are associated with reddish surfaces elsewhere in the outer solar system, including Pluto. If tholins are responsible here, the color could represent the accumulated chemistry of radiation acting on exposed surface material. Another explanation reaches deeper. The ancient collision that transformed Haumea may have removed much of its outer ice, leaving one region thinner than the rest. If rocky material lies closer to the surface there, the spot could be a lasting scar from that immense event. A third possibility involves sublimation, the direct transformation of solid ice into gas without passing through a liquid stage. If certain icy materials were selectively lost from one region, less volatile material could remain concentrated at the surface, producing a darker appearance. None of these explanations has been confirmed. That uncertainty comes from distance. We can measure changes in reflected light, but we cannot collect a sample, photograph individual grains, or place an instrument beside the region. The information reaching Earth has traveled across billions of miles before entering a telescope. Even so, the spot has a useful rhythm. It rotates with Haumea, appearing in the brightness record at the same 3-hour and 54-minute cycle as the rest of the body. That repeating pattern shows the feature is fixed to the surface rather than drifting independently through space. Its environment is extreme. Haumea's surface temperature is estimated near negative 402 degrees Fahrenheit, cold enough for water ice to behave as a rigid material rather than flowing like ice near Earth's surface. At such temperatures, the landscape would change incredibly slowly. Any exposed structure could preserve ancient evidence for immense stretches of time. The dark red spot, therefore, occupies an unusual position in our understanding of Haumea. We know where it is. We can measure how its light differs. We can watch it rotate through our observations. But its actual substance remains unresolved. A crystal carries a memory of order. Inside crystalline water ice, molecules settle into a repeating structure, arranged in a precise lattice that can preserve the history of how the surface formed. That structure should be difficult to maintain on Haumea. Energetic particles from the Sun and the wider galaxy have been striking Kuiper Belt surfaces for billions of years. Radiation damages the molecular arrangement of exposed ice, gradually turning ordered crystalline ice into amorphous ice, a disordered form in which the original lattice has been disrupted. Across many distant icy bodies, this process contributes to dark, radiation-processed surfaces. Haumea presents a striking contrast. Much of its surface retains crystalline water ice, suggesting that some process has exposed or produced fresh material during its long history. One possibility begins with gravity. Haumea's moons continually tug on their parent, creating changing stresses throughout the system. Tidal heating occurs when repeated gravitational flexing converts orbital and rotational energy into heat inside a body. If enough energy reaches Haumea's interior, it could help drive slow movement beneath the crust and periodically expose younger ice. Another possibility is cryovolcanism, the eruption of water or other volatile materials from an icy interior onto the surface. On a world this cold, such activity would look very different from volcanic eruptions on Earth. there would be no rivers of molten rock. Instead, material from below could rise through fractures and freeze across the surface. Rapid rotation provides another potential mechanism. The stresses associated with Haumea's extreme spin may create fractures through its icy exterior, opening pathways between buried material and the surface. Fresh ice could then replace regions altered by radiation. None of these mechanisms has been established as the answer. We are working from spectral evidence, gravitational models, and physical simulations rather than direct samples from the surface. The crystalline structure also tells us something about Haumea's past. Fresh crystalline ice can form through heating and subsequent cooling, irradiation under particular conditions, or geological processes that expose material from below. Its presence, therefore, suggests that Haumea's surface has experienced more change than its ancient age might imply. The temperature at the surface is around negative 402 degrees Fahrenheit. At such temperatures, water ice behaves more like a rigid mineral than the familiar ice beneath our feet, making ordinary surface flow extraordinarily unlikely. Yet deeper inside, conditions may once have been very different. Early in Haumea's history, radioactive elements released heat as they decayed, potentially warming its interior enough to alter ice and separate rock from lighter materials. That ancient warmth would have faded as those radioactive sources diminished. What remains today is a surface carrying crystalline ice across billions of years, preserving evidence that Haumea's interior once possessed a much more active thermal history than its present environment suggests. The ice, in other words, is more than a coating. It is a record of processes that reached from the surface toward the interior, and from Haumea's earliest history into the world we observe today. Long before Haumea became the frozen world we observe today, its interior may have been warm enough to behave very differently. During the first hundreds of millions of years after the solar system formed, newly assembled worlds retained heat from their formation and from radioactive elements embedded within their material. Among the most important were aluminum 26 and iron 60, unstable forms of elements whose nuclei gradually decayed. As they transformed, they released energy as heat. The process was slow compared with an explosion, yet powerful across geological time, allowing large bodies to warm from within. Haumea had enough mass and enough radioactive material to undergo this internal heating. Ice could melt, rock could begin moving. Gravity then took advantage of those differences in density. This process is called differentiation. Dense materials sink toward a body's center, while lighter materials rise outward, creating distinct internal layers. Haumea likely developed a rocky, silicate core beneath an outer region dominated by water ice. Its present density supports that picture. Haumea contains far more mass for its size than a body made mostly of water ice would contain, indicating a substantial rocky component within its interior. The later collision removed part of the lighter outer material, leaving the remaining body unusually rich in rock. Early Haumea may therefore have had an interior divided into layers, with heat moving through those layers and altering their physical state. At sufficient temperatures, water ice could have melted beneath the surface, creating a subsurface reservoir of liquid water. How long could such a reservoir survive? The answer depends on how much heat Haumea produced and how quickly that heat escaped. During its earliest history, radioactive decay would have supplied a stronger internal energy source than exists today. Over time, those unstable elements diminished, and the interior gradually cooled. If a liquid layer ever existed, it is now frozen. Haumea's relatively small size also made long-term heat retention difficult, allowing energy to escape into space across immense spans of time. The traces of that ancient warmth would remain in the structure we can measure today. A dense, rocky interior, an icy exterior, and a body whose composition is distinctly separated into layers all point toward a world that experienced substantial internal evolution. There is something especially useful about this history. We cannot open Haumea and examine its interior directly, yet its density, surface composition, rotation, and impact debris allow us to reconstruct parts of what happened beneath the surface. The frozen exterior therefore preserves more than ancient ice. It preserves evidence that Haumea once possessed a different internal environment, when radioactive decay was stronger and heat could still reshape the young world from within. That early transformation also matters because it gave the later collision a layered body to disrupt. When the impact eventually arrived, it encountered an interior already organized by billions of years of gravity and heat. The outer solar system was once a much more unsettled place than its present architecture suggests. Giant planets occupied different regions, debris crowded the spaces between them, and gravity continually altered the paths of countless frozen worlds. Jupiter, Saturn, Uranus, and Neptune formed from the same young disk, but their early arrangement was more compact. As they interacted gravitationally with surrounding material, their orbits gradually changed. Neptune, in particular, moved outward, scattering smaller bodies ahead of it and disturbing populations that had once followed more stable paths. This broad picture is described by the Nice model, a framework developed by planetary scientists in Nice, France. It proposes that the giant planets migrated substantially during the solar system's youth, rearranging the outer debris disk as their gravitational influence spread through it. For the objects beyond Neptune, migration meant disruption. Some were thrown inward, joining populations that may have contributed to the late heavy bombardment, a period when the inner solar system experienced unusually frequent impacts between roughly 4.1 and 3.8 billion years ago. Others remained farther out, but their orbits became more eccentric and inclined, carrying them across regions occupied by neighboring objects. That change matters for Haumea. A collision requires more than two bodies occupying the same distant region. Their paths must intersect, and their relative motion must bring them together with enormous energy. During this era, gravitational reshuffling created exactly those conditions across the Kuiper Belt. Some of the largest objects could suddenly find themselves on crossing trajectories. A world traveling through one orbital corridor might encounter another body whose path had been altered only recently. The distances were immense, yet the number of objects was also enormous, giving gravity countless opportunities to arrange destructive encounters. Haumea's ancient impact fits naturally within this unstable setting. A large Kuiper Belt object appears to have crossed its path and struck at an angle, transferring angular momentum while removing substantial icy material. The resulting debris eventually became associated with Haumea itself, its moons, its ring, and a broader collection of related bodies. That collection is known as the Haumea family. Its members share unusual surface properties and orbital characteristics that distinguish them from much of the surrounding Kuiper Belt. When scientists model their past motions, the group points toward a common origin, consistent with a major collision roughly 4 billion years ago. The timing connects Haumea to a remarkable chapter in planetary history. Its strange rotation and scattered family are remnants of an era when the giant planets we're still rearranging the solar system around them. Today, the planets occupy far more orderly paths. The evidence around Haumea preserves an older architecture, one shaped by migration, gravitational instability, and collisions. Its family remains one of only two confirmed collisional families known in the Kuiper Belt, giving astronomers a rare record of how violence once reshaped the distant solar system. Across the Kuiper Belt, Haumea has left behind something resembling a family tree written in orbital motion. At least 11 known objects share a connection that reaches back roughly 4 billion years, despite having spent ages drifting through separate paths. For astronomers, membership requires more than simply traveling nearby. Each object must occupy an orbit with closely matching characteristics, including its average orbital distance, orbital shape, and orbital tilt. Their surfaces must also resemble Haumea's, particularly through the presence of crystalline water ice. Spectral observations add another layer, revealing matching patterns in how these objects reflect different wavelengths of light. Together, those signatures form a remarkably specific fingerprint. 11 unrelated objects would be extraordinarily unlikely to develop the same orbital history and surface composition independently. Those similarities instead point toward a shared origin, fragments separated from a much larger parent during the ancient collision. Their shared ice makes that connection especially valuable because composition can survive long after orbital paths have changed. The combined mass of the currently recognized family members is estimated at roughly 2% of Haumea's present mass. That fraction may represent part of the icy material excavated from Haumea's outer layers and scattered into surrounding space. Some fragments remained large enough to become independent worlds, while countless smaller pieces may have followed less noticeable paths. 4 billion years of orbital evolution have stretched the original pattern across enormous distances. Gravitational encounters with Neptune and other distant bodies slowly alter trajectories, yet the family resemblance remains detectable. For us, that persistence is remarkably useful because orbital motion preserves information long after the event itself has vanished. Scientists can run gravitational simulations backward through time, testing how the known members could have separated after the impact. By comparing those simulated histories with their present positions, researchers can constrain the collision's timing, relative velocity, and likely geometry. The family therefore acts as a natural record of an event no telescope ever witnessed. There is another discovery hidden within the fragments. Their water ice rich surfaces suggest that large bodies forming in the early Kuiper Belt developed substantial icy outer layers. That evidence helps scientists reconstruct the chemistry of the distant region where these worlds assembled, offering clues about how water and other materials were distributed during the solar system's formation. Yet the catalog is almost certainly incomplete. Smaller family members can be extremely faint, especially against the sparse background of distant space. Some may remain below the detection limits of current surveys, still circling the Sun with their origins preserved in their orbital paths and their ancient ice. The family records the material Haumea lost. What remains inside Haumea records something different. The part of the world the collision exposed, leaving astronomers with an unusual glimpse into an interior that would otherwise have stayed hidden. A glance at Haumea's mass tells us something unusual about its history. Its density is about 2.6 grams per cubic centimeter, far above pure water ice at roughly zero point 0.9 grams per cubic centimeter and higher than the typical mixture found across many Kuiper Belt objects. That difference is more than a measurement, it is evidence of separation. Most small, icy worlds formed as mixtures of rock and ice, without enough internal heat or gravity to arrange their materials into distinct layers. Haumea appears to have undergone differentiation much more strongly, leaving dense silicate rock concentrated toward its center beneath a comparatively thin icy shell. Then the ancient collision changed the equation. A substantial portion of that outer ice was blasted away, exposing material from deeper inside. In effect, Haumea became a naturally occurring cross-section of a differentiated world. We can infer the interior without drilling through the surface or sending instruments into its depths. The rocky component is thought to resemble silicate material found in the deeper regions of Earth and Mars, although Haumea's environment is vastly colder. Its remaining surface is dominated by nearly pure water ice, creating a sharp contrast between the dense interior and the frozen exterior. That structure also changes the experience of standing there. Haumea's gravity is unusually weak, and its rapid rotation makes the difference even greater. Near the poles, surface gravity is about 0.063 times Earth's gravity. Around the equator, it can fall to roughly 0.017 times Earth's gravity. Imagine weighing 180 pounds on Earth. Depending on where you stood, your weight on Haumea could be only about 3 to 11 pounds. Movement would become strange as well. A strong horizontal jump at the equator could carry you hundreds of feet above the surface, followed by a long descent through Haumea's weak gravitational field. The rotation adds another complication because centrifugal effects reduce the effective pull holding you down. Near the equatorial limit, the distinction between jumping and escaping becomes remarkably small. A sufficiently energetic leap in the right direction could potentially send an object onto an orbit around Haumea rather than returning it to the ground. For you, the landscape would therefore be unlike anything familiar on Earth. The ground beneath your feet would belong to a world whose outer layers were violently removed billions of years ago, exposing a composition that normally remains buried. Yet there is a fundamental limitation. We have never actually stood there, photographed its terrain, or examined its rocks directly. Every detail comes from measurements gathered across billions of miles. Haumea has revealed its mass, shape, rotation, moons, ring, and fragments. Its surface remains an inferred landscape, reconstructed from light and gravity. Whether that changes someday depends on a difficult question, because reaching Haumea would demand a journey unlike almost any planetary mission ever attempted. Everything we know about Haumea has arrived through light. No human instrument has touched its surface, entered its orbit, or measured its rocks directly. For us, the world exists through photons carrying faint information across roughly 4 billion miles of space. Those photons reach telescopes on Earth after reflecting from an object we have never visited, preserving subtle clues about its shape, motion, temperature, and composition. One of the most powerful clues comes from Haumea's changing brightness. Light curve analysis measures those fluctuations as the world rotates, allowing scientists to reconstruct its rotation period and unusual, elongated shape. The pattern repeats with remarkable consistency. Spectroscopy adds another layer. This technique spreads reflected sunlight into its component wavelengths, revealing chemical fingerprints hidden within the light. From those patterns, researchers identified water ice across Haumea's surface and recognized differences within the mysterious dark region. Then there is the stellar occultation. When Haumea passes in front of a distant star, the star's light disappears and returns at precisely measurable moments. By comparing those timings from different locations on Earth, astronomers can reconstruct Haumea's silhouette with extraordinary precision. Heat provides another clue. Thermal infrared observations detect the faint radiation emitted by Haumea itself, helping scientists constrain its surface temperature and the amount of sunlight its surface reflects. Even without touching the world, heat becomes another measurable property. The moons provide yet another path into the unknown. By repeatedly tracking their positions against distant stars, astronomers can measure tiny changes in their orbits. Gravitational modeling then reveals Haumea's mass, because the moons respond directly to the gravity of their parent. Five different techniques, one distant world. Together, they have transformed faint points of light into an increasingly detailed physical model. And still, no spacecraft has reached Haumea. There is currently no funded mission traveling there, and no spacecraft has entered development for a Haumea encounter. Using propulsion comparable to present deep space missions, a journey could require roughly 16 to 20 years, depending on trajectory and launch conditions. That would already exceed the duration of many planetary missions. New Horizons required about 9.5 years to reach Pluto, despite traveling toward a destination considerably closer to the Sun than Haumea. A European Space Agency mission concept known as Kronos once explored the possibility of visiting the distant world, but it did not advance into an approved mission. The distance remains only one obstacle among many. Without a spacecraft, entire categories of information remain inaccessible. We do not know Haumea's surface topography, the precise chemistry of its dark region, or whether geological activity continues today. The detailed interiors of its moons remain unknown, as does the exact composition of its ring particles. Even additional small moons could still be hidden from our current observations. Everything we have learned has come from observing, measuring, modeling, and interpreting light. Yet, Haumea's discovery itself revealed that even distant light can become a source of controversy, because almost immediately after the world was recognized, astronomers began disagreeing over who had truly found it. Scientific discovery can become complicated when priority arrives before certainty. Haumea entered that uncertainty in May 2004, when Mike Brown's team at the California Institute of Technology first observed the distant object using the Palomar Observatory. Their observations came long before the world was publicly announced. Yet the discovery had not been formally submitted to the International Astronomical Union's Minor Planets Center, leaving the scientific record open to another claimant. On July 27, 2005, Jose Luis Ortiz Moreno and his colleagues at the Sierra Nevada Observatory in Spain submitted their own discovery claim. Their observations had independently identified Haumea, but the timing immediately changed the story. Within hours, Brown's team submitted its own claim. They pointed to observations made 14 months earlier, establishing a substantially earlier observational date. Then came the accusation. Brown alleged that Ortiz's team had accessed publicly available observation logs maintained by the California Institute of Technology. Those logs contained enough information to reveal where the object had been observed, potentially allowing another team to locate it before submitting a claim. Web server records became part of the dispute. Brown reported that the California Institute of Technology website had been accessed from an internet address associated with Ortiz's institution shortly before the Spanish announcement. Ortiz rejected the implication that this amounted to obtaining another team's unpublished discovery. His position was that the access was routine and that the Spanish observations were independently conducted. The International Astronomical Union eventually resolved the naming question without formally deciding every aspect of the accusation. Its decision recognized Brown's team through the earlier observational date and granted that team the right to propose the object's official name. They chose Haumea. honoring a Hawaiian goddess associated with fertility and childbirth. Ortiz's team had proposed Addisina, the name of an ancient Iberian goddess associated with the underworld. The disagreement left a complicated record behind. We can identify dates, observations, website access records, and official decisions, yet their meaning remains contested. That makes Haumea's discovery unusual in another way. The object itself became a lesson in how modern astronomy actually works, where distant worlds may be found through years of patient observation, but scientific priority can depend on what happens before those observations ever become public. For you, the controversy also changes how we interpret the name attached to this distant world. Behind it lies a dispute involving competing teams, national institutions, public records, and the unwritten rules that hold scientific collaboration together. Yet beyond the argument, the discovery itself remains extraordinary. Haumea was unlike the other distant worlds known at the time, rotating with remarkable speed and carrying physical clues to a violent ancient history. To understand just how unusual that made it, we have to place Haumea beside the dwarf planet that became the benchmark for the outer solar system. Place Pluto beside Haumea, and the contrast begins before either world moves. Both travel through the distant Kuiper Belt, yet their physical stories could hardly be more different. Pluto is roughly 1,477 miles across, large enough for gravity to pull it into a nearly spherical shape. Haumea stretches about 1,218 miles along its longest dimension, while its shortest reaches only 619 miles. Its rapid rotation has distorted the entire body into an elongated form. The difference becomes even clearer with time. Pluto turns once every 6.4 Earth days. Haumea completes a rotation in only 3.9 hours, spinning nearly 40 times faster. That extraordinary rate is central to its shape, keeping material farther from the center, moving at tremendous speed. Mass separates them further. Pluto contains roughly 3 times as much material as Haumea, giving its gravity much greater influence over its surroundings. Yet size alone does not explain the character of either world. Look at their atmospheres. Pluto possesses a thin nitrogen atmosphere that changes as sunlight warms and cools its surface during its journey around the sunday. Haumea shows no detectable atmosphere, leaving its exposed surface directly subject to the conditions of deep space. Their surfaces tell different stories, too. Pluto carries nitrogen, methane, and carbon monoxide ices across broad plains and mountainous terrain, with regions shaped by processes that continue today. Haumea presents something much simpler, chemically dominated by water ice, interrupted by the unusual dark region we have already encountered. Then there are their moons. Pluto has 5 known satellites, including Charon, which measures about 750 miles across. Charon is so large relative to Pluto that the pair behaves differently from an ordinary planet and moon system. Haumea's 2 moons are much smaller, and their compositions connect them directly to the violent history of their parent. Even their geological timelines diverge. Pluto preserves evidence of nitrogen glaciers, possible cryovolcanic activity, and surfaces that appear surprisingly young in places. Haumea carries stronger evidence of an ancient transformation, with its present structure shaped largely by a collision billions of years ago. So when you place these 2 dwarf planets together, you are really comparing 2 different kinds of planetary history. Pluto resembles a world whose surface continues to change, while Haumea preserves the physical consequences of an ancient catastrophe, and both remain only fragments of the larger Kuiper Belt. Beyond them lies a vast population of distant bodies, many too faint, small, or remote for detailed study. Haumea, therefore, becomes something more than an unusual dwarf planet. It becomes one precise clue within a much larger region we are still learning to understand. Beyond Haumea, the solar system becomes increasingly difficult to count. The Kuiper Belt contains hundreds of known objects larger than 60 miles across, yet surveys suggest hundreds of thousands may exist at that scale or larger. Then there are the smaller bodies. Their numbers could reach into the hundreds of millions, perhaps even approaching a trillion, depending on how small an object we include. Most remain invisible to present surveys, scattered across enormous distances and moving through a region we have only partially explored. Among the better-known worlds are Pluto, Eris, Makemake, Haumea, Quaoar, Sedna, and Gonggong. Each occupies a different orbital path, and each preserves another piece of the solar system's early history. Haumea is unusual, even among them, because its physical structure records a collision with exceptional clarity. Eris carries a different kind of importance. Discovered in 2005, it is almost the same size as Pluto and more massive. Its discovery forced astronomers to confront a difficult question. How many planets could the solar system contain? When the International Astronomical Union established the category of dwarf planets in 2006, Pluto was reclassified. Eris became part of the same group, showing how one distant discovery could reshape the definition of a planet throughout astronomy. Farther out, Sedna presents an even stranger problem. Its closest approach to the Sun is roughly 7.6 billion miles, placing it far beyond the main Kuiper Belt. One complete orbit takes approximately 11,400 years. We have no complete explanation for that path. One possibility is that a passing star disturbed Sedna during the solar system's youth. Another proposes the influence of a massive object that may still remain undiscovered in the distant outer solar system. That possibility connects to the Planet 9 hypothesis. Several distant Kuiper Belt objects appear to have orbital orientations that cluster more strongly than some models would expect from random distribution. A hypothetical planet between 5 and 10 times Earth's mass could produce such gravitational effects. But Planet 9 has never been directly observed. The hypothesis remains unconfirmed, and astronomers continue searching the darkness for evidence. Haumea, therefore, occupies an interesting position within this enormous population. We know its dimensions, rotation, moons, ring, surface composition, and unusual history with unusual precision. Yet even Haumea represents only one member of a vastly larger family of worlds. The farther we look, the more incomplete our map becomes. Beyond the Kuiper Belt lie scattered populations, distant reservoirs of icy bodies, and regions where the sun's influence gradually weakens across immense stretches of space. For you, Haumea can seem remote beyond imagination. Yet on the scale of the solar system, it is only one landmark among countless others. And the farther those landmarks extend, the less certain we become about where the solar system truly ends. Haumea sits roughly 4 billion miles from the Sun, far beyond the familiar worlds of the inner solar system. At that distance, even light needs approximately 6 hours to cross the space between the Sun and Haumea. Light travels faster than anything else known, yet across this enormous distance, its journey is measured in hours. Imagine driving toward Haumea at 65 miles per hour, never stopping for fuel, rest, or repairs. The journey would last roughly 7,000 years, longer than the entire span of recorded human civilization. Spacecraft move much faster. The New Horizons spacecraft reached Pluto after traveling for about 9.5 years, moving at speeds exceeding 36,000 miles per hour. At that same speed, reaching Haumea would still require roughly 17 years. Distance changes the meaning of observation. Every telescope measurement we have ever made of Haumea began with light leaving that distant world, crossing billions of miles, and finally reaching instruments near Earth. Those photons carried information about rotation, composition, shape, and motion. We never touched the object producing them. The discovery of Haumea's ring makes that precision even harder to imagine. In 2017, 12 telescope stations across several countries watched the same distant star as Haumea passed across its light. The expected pattern was straightforward. The star disappeared as Haumea crossed in front of it, then returned as the body moved onward. But tiny interruptions appeared before and after the main occultation. Each lasted only a few seconds, yet their timing matched across multiple observing stations. From roughly 4 billion miles away, astronomers had detected material orbiting around an object they could not directly see. That ring spans about 43 miles. Its discovery depended on measuring changes in starlight, lasting only moments. You can trace the entire investigation back to this same principle. Haumea's shape emerged from changing brightness. Its surface composition emerged from reflected wavelengths. Its dimensions emerged from a star disappearing behind its silhouette. Its moons revealed the object's mass through their gravitational motion. Even its surface temperature came from radiation reaching instruments across space. Every clue began as light. That means the Haumea we know is a reconstruction assembled from distant signals. There is no spacecraft photograph of its terrain, no instrument touching its ice, and no probe measuring the material beneath its crust. Instead, we have learned to read the smallest changes in brightness, color, timing, and motion. Across billions of miles, those changes become measurements. The remarkable part is not simply that Haumea is distant. It is that distance has not prevented us from discovering its history. We have never stood there. We have never watched its surface directly. Yet from Earth, we have reconstructed an elongated world, 2 moons, a ring, crystalline ice, and the physical evidence of an ancient collision. All of it began with photons crossing the dark between worlds. Nothing in the universe remains unchanged forever, and Haumea is no exception. Its extraordinary rotation, preserved across immense stretches of time, is already being altered by the gravitational relationships around it. Every orbit carries an exchange of energy. Haumea raises tidal bulges within Hi'iaka and Namaka, while those moons exert their own gravitational influence back upon Haumea. Tides are deformations caused by gravity, and their continual movement allows rotational energy to leak slowly into the orbital motion of the system. The process is extraordinarily gradual. Across human history, Haumea's rotation would appear essentially unchanged. Yet, over hundreds of millions or billions of years, even a tiny transfer can accumulate into a major transformation. Eventually, the system could approach tidal locking. This occurs when a body's rotation period becomes equal to the orbital period of its companion, causing the same side to face that companion continuously. Our moon provides the familiar example. For Haumea, such an outcome would radically change the rhythm of its rotation. If Hi'iaka became the dominant tidal influence and Haumea eventually matched its roughly 49.5-day orbit, the dwarf planet would turn once every 49.5 days instead of every 3.9 hours. That difference would reshape the forces acting upon its body. Much of Haumea's present elongation comes from centrifugal effects produced by its rapid rotation. Slow the rotation enough, and those effects would weaken dramatically. Given sufficient internal mobility, the body could then begin relaxing toward a more rounded form. That process would take extraordinary lengths of time, with ice and rock responding gradually to gravity and internal stress. The ring faces its own uncertain future. Particles orbiting close to small worlds can collide, spread, migrate, or gather together under gravity. Over hundreds of millions to billions of years, such processes can gradually transform a ring into dispersed material or even contribute to the formation of another small moon. Haumea itself would change far more slowly. For millions of years, an observer returning again and again would find essentially the same rotating world, even as imperceptible gravitational exchanges continued beneath the surface of its system. Eventually, the sun will change too. In roughly 5.4 billion years, it is expected to expand into a red giant, dramatically increasing the amount of energy reaching the outer solar system. Haumea will remain far from the sun, but greater solar heating could alter its surface. Frozen materials may begin sublimating more actively, while regions preserved for billions of years could undergo chemical and physical changes. The transformation would unfold across timescales almost impossible for a human life to comprehend. A world shaped by an ancient collision would slowly surrender its rapid spin, its ring would evolve, and its surface would respond to a changing Sunday. Long after humanity is gone, Haumea may still remain recognizable as a distant icy body, carrying the scars of an ancient collision through a solar system that itself has become almost unrecognizable. Far from the warmth of the sun, water survives in a form we rarely see on Earth. Haumea carries vast quantities of water ice across the outer solar system, preserved where temperatures remain low enough for ice to endure over immense spans of time. That matters because water is more than a familiar substance. In liquid form, it provides an environment where dissolved chemicals can move, interact, and build increasingly complex structures. Much of the chemistry associated with life depends upon those interactions, making water central to our understanding of habitable environments. Haumea shows that water can remain abundant, even billions of miles from the Sunday. Its surface ice is remarkably rich in water, and the fragments belonging to its collisional family carry similar material through their own distant orbits. Those fragments do not remain perfectly fixed forever. Gravity from Neptune and the other giant planets continually alters the paths of small bodies, sometimes nudging them into new orbital arrangements over enormous periods. Given enough time, some icy objects from the outer solar system can be redirected toward the inner regions. We see the results in comets, whose journeys can carry frozen material across vastly different parts of the planetary system. Could some of that material have contributed to Earth's water? The possibility has been studied for decades. Models of planetary formation indicate that Earth formed relatively close to the young Sun, where temperatures made it difficult for large quantities of water ice to remain during the earliest stages of assembly. Additional water, therefore, had to arrive through later delivery, although the exact sources and proportions remain debated. Earlier impact eras may have provided opportunities for water-rich bodies to strike the growing planets. Some models have considered contributions from asteroids, while others allow for material originating farther out, including primitive objects from the outer solar system. Haumea does not provide a direct shipment route to Earth. Its significance is subtler. It gives us evidence that enormous stores of water ice existed in the distant solar system, and that violent collisions could redistribute that material into families of smaller bodies. Those fragments then became part of a much larger population governed by gravity. Over geological time, their paths can change, linking distant reservoirs with regions much closer to the Sunday. The connection between Haumea and Earth's oceans therefore remains indirect. We cannot trace a particular molecule of water from Haumea to our planet, and current evidence does not establish Haumea as a major source of Earth's water. What Haumea does reveal is the scale of the reservoir. Water was present throughout the young solar system, locked into worlds that formed far beyond the terrestrial planets, where ice could persist for billions of years. When we look at Haumea, then, we are studying more than an unusual dwarf planet. Its ice is evidence of how planetary materials were stored, transformed, scattered, and sometimes transported across enormous distances. And that raises a larger question about the worlds formed from those materials. If water can travel through such a vast planetary system, then perhaps the boundaries between different kinds of worlds are less permanent than they appear. A category can be useful until nature produces something it cannot comfortably contain. Haumea occupies that uncomfortable space, where the language of planetary science begins to reveal its limits. The International Astronomical Union established its formal definition of a planet in 2006. A planet must orbit the Sun, possess enough gravity to reach hydrostatic equilibrium, and clear the region around its orbit of comparable bodies. Hydrostatic equilibrium means gravity has reshaped the object into a stable form, balanced against the forces acting within it. Haumea satisfies the first condition. It satisfies the second in a more complicated way. The third is where it fails. That final requirement places Haumea among the dwarf planets. Yet the shape that makes Haumea so unusual comes from the same physics behind hydrostatic equilibrium. Its rapid rotation creates centrifugal effects that oppose gravity around the equator, stretching the body outward. Instead of settling into the familiar rounded form, Haumea occupies a highly elongated equilibrium shape. That distinction matters. A world does not need to resemble Earth, Pluto, or the Moon to be governed by the same physical principles. In Haumea, rotation has become strong enough to transform the balance between gravity and internal structure, producing a body whose proportions seem almost improbable when viewed beside ordinary planets. You can think of the shape as a physical record of motion. Every hour of Haumea's rotation contributes to the forces maintaining its present form, while its mass and composition determine how strongly the material responds. The result is not an arbitrary deformation. It is the stable outcome of a particular combination of density, gravity, and rotation. This is where Haumea becomes more than an unusual entry in a catalog. It is differentiated internally, surrounded by moons, encircled by a ring, and marked by geological history that reaches back billions of years. Its surface chemistry preserves evidence of ancient processes, while its present structure records the consequences of extraordinary rotational speed. The word world can therefore become useful in a broader sense. We use categories because they help us organize what we discover, but those categories are descriptions created by people, not boundaries imposed by nature. Haumea does not become less of a world because its shape challenges an expectation. Its strange geometry is precisely what makes its physical history legible. The egg-like body tells us about rotation, internal structure, and the forces that have acted upon it since its formation. And perhaps That is the more revealing lesson. When we look beyond the familiar planets, we find that a world can take forms our definitions never anticipated. Haumea simply occupies one of those possibilities, suspended in the outer solar system, where gravity, rotation, ice, and time have combined into something entirely its own. Names usually arrive after discovery, chosen to give a distant object some connection to human culture. In Haumea's case, the connection reaches further than anyone could have expected. The International Astronomical Union follows naming traditions for distant Kuiper Belt objects, drawing from mythologies connected with creation, fertility, or the underworld. Haumea received a name from Hawaiian tradition, where Haumea is associated with childbirth, fertility, and the earth. That association becomes remarkably fitting when we consider what the dwarf planet actually is. Haumea's present form was shaped by an ancient collision, and material removed from its outer layers became part of a family of orbiting bodies. Its moons therefore preserve a physical connection to their parent, carrying material that once belonged to Haumea itself. There is another layer to the mythology. Haumea is described as a shapeshifter, capable of changing her form and appearing differently from one observer to another. Scientifically, Haumea seems to echo that idea in an unexpected way. Its shape is unlike the rounded form we usually imagine for a dwarf planet. Rapid rotation stretches the body into an elongated equilibrium figure, making its outline fundamentally different from worlds such as Pluto. The transformation is physical, governed by gravity and rotation, yet the mythological image of changing form feels almost strangely appropriate. Even the moons continue the pattern. Iaka, the larger moon, takes its name from a daughter of Haumea in Hawaiian mythology. According to the tradition, Hi'iaka was born from between Haumea's fingers and became associated with the island of Hawaii, healing, and journeys. Namaka carries another connection. In Hawaiian mythology, Namaka is a sea goddess, sister of Hi'iaka and another daughter of Haumea. Her scientific counterpart is the smaller moon, moving on a more eccentric orbit and responding to the gravitational relationships within the system. The parallels become difficult to ignore. A mother gives rise to children, and the children remain connected to their origin. In the physical system, Haumea's outer material became moons and fragments, while their compositions preserve clues about the body from which they came. Yet the naming committee could not have known how closely these stories would resemble the physics. The names were selected from an existing cultural tradition, while the scientific relationships emerged from observation and analysis. So the resemblance is coincidence. Still, coincidence can be revealing. When we place mythology beside astronomy, we are reminded that humans have always used stories to understand unfamiliar worlds. The difference now is that our stories are accompanied by measurements, spectra, orbital models, and light gathered across billions of miles. Haumea carries both kinds of meaning at once. Its name comes from an ancient story about transformation and birth, while its physical history describes a body transformed by violence and surrounded by children born from its own material. Somewhere between those two stories, the name becomes more than a label. It becomes an unexpectedly precise echo of what this strange world has actually become. 20 years of observation can make a distant world seem familiar, yet familiarity becomes misleading when the evidence comes from so many indirect clues. Haumea is among the better characterized objects beyond Neptune, studied with powerful telescopes on Earth and in orbit, but much of its physical story remains unresolved. The dark red region remains especially difficult to explain. We know it differs from the surrounding ice, yet its exact composition remains uncertain. Possibilities include radiation-altered organic material, a concentration of darker minerals, or material associated with an ancient impact. Each explanation fits some observations. None has been confirmed. Deeper questions become harder. We still cannot determine the precise thickness of Haumea's icy shell or describe the boundary between that layer and its rocky interior with certainty. The possibility of present geological activity is also unresolved, leaving open whether internal heat might still move through the body or occasionally alter its surface. Even the ring remains partly mysterious. Its particles have been detected through their effects on starlight, but their exact sizes, compositions, and ages remain uncertain. Additional small moons could also exist close to Haumea, hidden by glare or simply too faint for current instruments to separate from their parent. The two known moons hold unanswered questions of their own. We can calculate their orbits and use those motions to understand the system's mass, yet their internal structures remain largely inaccessible. Are they solid bodies with distinct layers, or loosely assembled collections of fragments? Light gives us clues, but no direct inspection. Then there is the ancient collision that shaped so much of the system. We can model possible impact scenarios, but the exact timing, angle, speed, and size of the impactor remain uncertain. Different combinations can reproduce portions of the evidence, leaving the original event partly hidden behind billions of years of orbital evolution. Perhaps the most intriguing uncertainty lies on the surface itself. Crystalline ice should gradually lose its ordered structure under prolonged radiation, yet Haumea retains that unusual signature. We have several possible explanations, including resurfacing and internal activity, but no single mechanism has been demonstrated as the answer. Almost everything we know was assembled within the last 2 decades. We have built this picture from Earth and from space, using measurements of light, timing, motion, and gravitational influence rather than direct contact. That distinction matters. A detailed model can still contain enormous gaps. Haumea reminds us that discovery and understanding are different stages. Finding a world gives us a name and a place to begin. Studying it gives us patterns, measurements, and competing explanations. Those unanswered questions remain part of the result. Beyond Neptune, countless bodies have never been visited, measured closely, or even identified. The outer solar system remains less like a completed map than a region filled with blank spaces. And those blank spaces are not evidence that science has failed. They show where observation ends and investigation begins, leaving us with something more valuable than certainty, a precise understanding of what remains unknown. For most of human history, the outer solar system had no place in human thought. There was only the sky we could see. Then, in 1992, David Jewett and Jane Liu identified an object beyond Pluto, giving the Kuiper Belt its first confirmed member. Suddenly, the region beyond Neptune became more than a theoretical frontier. It became a population of worlds, fragments, and frozen remnants waiting to be found. Haumea arrived later, in 2004, after billions of years of existence without an observer. During that immense interval, continents rose and changed on Earth, species appeared and disappeared, and human civilizations emerged and vanished. Through all of it, Haumea continued along its orbit. Nothing about the object depended on discovery. Its rapid rotation followed the same physical laws long before any telescope recorded it. Its moons circled their parent through ages when Earth had no cities, no written language, and no one looking toward that distant region. That distinction gives discovery an unusual meaning. We often speak as though finding something brings it into existence within our understanding, yet the physical reality came first. The evidence was already encoded in motion, reflected light, gravitational effects, and the passage of time. You can imagine Haumea existing through generation after generation, real and unknown. Human beings could have searched the sky for thousands of years without finding it because the necessary instruments and scientific questions did not yet exist. The Kuiper Belt itself shows how much our cosmic map depends on technology. Before the 1990s, almost everything beyond Neptune remained observationally inaccessible. Improved detectors, digital imaging, larger telescopes, and better methods gradually turned faint points of light into recognizable populations. Haumea became part of that transformation. Its discovery did not alter its shape, orbit, or history. Instead, it altered the human record, adding another physical object to the universe we know exists. The universe does not become larger when we discover something. Our knowledge does. Each new world changes the questions around it. One discovery leads to another, until an apparently empty region becomes crowded with objects carrying distinct histories. We are still living through that process. Much of what exists beyond Neptune has never been observed closely, and some bodies may remain too faint for present instruments. Yet every one of them is already there. Discovery, then, is a peculiar human act. We do not create the distant world. We create a relationship with it through observation, measurement, and imagination constrained by evidence. Haumea spent billions of years needing nothing from us. Its existence was complete without a name, a telescope, or a human witness. And now, somehow, we know it is there. We can trace its motion, reconstruct fragments of its history, and recognize the strange physics written across its distant form. In doing so, we have changed something far beyond Haumea itself. We have changed the scale of what the human mind can include when it looks into the dark. There is something unusual about looking at Haumea from Earth. The distance itself is extraordinary, but the observer is stranger still. Across the solar system, matter follows gravity, collides, freezes, melts, fragments, and rearranges itself. Worlds form from those processes. Moons settle into orbits, and rings spread into thin bands of particles. Yet, as far as we currently know, only one world contains matter capable of understanding what any of this means. That world is Earth. The distinction begins with chemistry. The atoms inside your body existed before you did, forged through ancient stellar processes and scattered through space before the sun and planets formed. Those same cosmic materials eventually became rocks, oceans, atmospheres, living cells, and nervous systems. Somehow, matter became capable of observing itself. You can look toward Haumea and understand that its shape comes from physical laws. You can follow evidence across decades and reconstruct events that happened billions of years ago. You can recognize that its rotation affects its form, that gravity governs its companions, and that distant photons can carry information across the solar system. Haumea does none of this. Its surface responds to sunlight. Its interior responds to gravity. Its moons continue along their paths. The object changes according to physics, without any apparent awareness that it exists. That difference is difficult to place into ordinary language. We usually think of matter as something observed from outside, something measured and described. Consciousness introduces another possibility, where part of the physical universe becomes capable of building an internal model of the universe around it. We still do not know why that happens. We do not know whether consciousness is extraordinarily rare, whether simple life is common, or whether complex minds appear frequently on planets throughout the galaxy. Earth is the only example currently available to us, so every conclusion begins with a single known case. And that makes every observation of Haumea strangely intimate. A telescope gathers photons that have traveled across billions of miles. Instruments separate those photons into patterns. Computers compare measurements. Scientists turn those patterns into estimates of shape, composition, motion, and history. Then, a human mind interprets the result. You can sit here, on a small planet near an ordinary star, and picture a distant body whose existence predates humanity by billions of years. The object itself has no need for the story we construct around it. The story exists because we are capable of asking what it means. Perhaps that is the most unusual thing about planetary science. We are studying worlds that cannot study themselves, using matter that somehow became capable of studying anything at all. Haumea does not recognize its own strangeness. Its shape is simply the consequence of mass and rotation. Its moons are simply consequences of gravity and history. The recognition belongs to you. For a brief moment, the solar system contains something extraordinary, a distant world being understood by another world through a chain of light, matter, mathematics, and consciousness. And somewhere within that chain, the universe has produced an observer capable of looking outward and realizing that it is looking. Haumea can be reduced to a handful of physical facts, yet those facts describe a world unlike almost anything else we know. Its longest dimension is roughly comparable to the width of California, while its rapid rotation keeps its body stretched far beyond the spherical form gravity usually creates. Its shape is therefore a physical record of motion, preserved across unimaginable spans of time. Billions of years ago, a collision transformed that world. Material was stripped away, fragments remained in orbit, and the resulting system acquired moons and a ring. The event belongs to a distant past, yet its consequences are still written into Haumea's present structure. Its surface adds another layer of uncertainty. Water ice covers much of the body in an unusually crystalline form, while a dark red region remains unexplained. We can identify the ice from the way it interacts with sunlight, but the precise nature of that darker material remains beyond our reach. For billions of years, Haumea continued its rotation without any human witness. Earth changed around the Sunday. Life became increasingly complex. Civilizations appeared, disappeared, and left records behind. Haumea simply followed its orbit. Then, only about 20 years ago, human instruments finally noticed it. Its discovery came through changes in brightness as the object rotated. Later, observations of a distant star passing behind Haumea revealed the presence of its ring, with telescopes separated across Earth recording the brief changes in starlight. Those measurements are remarkable for another reason. We have never sent a spacecraft there. No instrument has touched its surface. Every estimate of its form, composition, rotation, and surrounding system has been reconstructed from distant evidence. Even now, important pieces remain missing. We do not know the exact nature of the dark region. We cannot map its surface directly. We cannot examine its interior or inspect the particles making up its ring. Our picture remains incomplete. Yet incompleteness does not make the picture meaningless. Each measurement places another constraint on what Haumea can be, narrowing the possibilities until a coherent physical world emerges from scattered signals. You can think of that knowledge as a sketch drawn across immense distance. It lacks the detail a visitor would see, but its essential structure is already there. Haumea was extraordinary long before humanity recognized it. It will remain so long after every person alive today is gone. The difference is simply that we now know its name, and perhaps that is enough to mark the strange achievement of discovery. A world that spent billions of years existing without witnesses has entered human knowledge, carried here by light, mathematics, patience, and curiosity. The sketch is incomplete. There are gaps we may never fill, but inside those gaps, something unmistakable remains. A real world, still turning. There has always been a line where knowledge thins into uncertainty. For ancient sailors, it waited beyond the horizon. For explorers crossing continents, it appeared where coastlines faded into blank paper. That boundary kept moving. Ships carried maps farther across oceans. Expeditions reached the poles. Telescopes extended human vision beyond Earth, and spacecraft eventually crossed the paths of distant planets. Each achievement shifted the frontier outward while revealing how much remained beyond it. Haumea belongs to this latest kind of frontier. We know its orbit, its rotation, its companions, and much of its unusual physical character. Yet no spacecraft has visited, and no camera has returned a close view of its surface. That distinction matters. A place can be mapped without being explored directly. We can infer its properties from light, motion, and gravity, building knowledge without ever standing there. Haumea, therefore, occupies an unusual position in the history of exploration. It has been recognized, named, and studied while remaining physically beyond our reach. The region around it is larger still. Beyond the main Kuiper Belt lies the scattered disk, where some objects travel on highly elongated and inclined orbits. Farther outward, scientists expect another vast population, the Oort cloud, a theoretical reservoir of icy bodies surrounding the solar system. We have never directly observed the Oort cloud as a whole. Its existence is inferred from the paths of long-period comets that enter the inner solar system from immense distances. Even our best map, therefore, contains regions drawn with different levels of certainty. Some boundaries are measured, others are modeled. Some remain almost entirely unexplored. Haumea sits within that layered map as a physical world we can study from afar. Its discovery showed that the outer solar system was more varied than earlier generations could have known, and every new object adds another piece to that changing picture. What happens when we reach one edge? Usually, another appears. The pattern has repeated throughout exploration. A coastline leads to another coast. A mountain range reveals valleys beyond it. A planet sends a spacecraft toward another planet, only for the distant frontier to become a new destination. Space follows the same pattern, though its distances are far greater. The edge of the map is therefore not a physical boundary. It is a measurement of our current ability to observe, travel, and understand. Beyond Haumea, there are objects too faint, too distant, or too slowly moving for us to recognize with certainty. Some may already have been captured in old observations without anyone realizing what they were. Others may remain completely unseen. You can think of exploration as an expanding circle of awareness. Its outer boundary keeps moving, while the unknown remains larger than the known. Haumea is part of that expanding circle. It is not the end of the planetary map. It is one point along its present edge, marking the place where our knowledge has reached and where the universe continues beyond it. While you are listening to this, Haumea is still turning. One rotation follows another, each completed in only a few hours, while the distant world continues along its enormous path around the Sunday. By the time you settle into sleep, Haumea may have rotated several more times. Its elongated body keeps presenting different regions toward the sunlight, while its ring and moons continue following the motions imposed by gravity. Hyakka remains in its broad orbit. Namaka follows its more complicated path. Both companions carry material connected to Haumea's ancient history, yet neither requires an observer to continue moving. Nothing waits for us. The outer solar system operates on timescales that make a human lifetime seem remarkably brief. Haumea takes hundreds of years to complete one journey around the sun, far longer than the span between several generations of people. Imagine watching from Earth for your entire life. You would witness only a small fraction of Haumea's orbital journey, while its rotation would continue thousands upon thousands of times. That difference in scale changes how we think about time. A human life is measured through seasons, birthdays, memories, and generations. Haumea's history is measured through collisions, orbital changes, radioactive decay, and the gradual evolution of a planetary system. Yet the underlying physics does not change with scale. The same conservation of angular momentum that governs a spinning object on Earth also describes Haumea's rotation. Gravity shapes its motion around the sun and influences the paths of its moons. Energy moves through the system according to rules that remain consistent across immense distances. Those rules were understood in pieces long before anyone knew Haumea existed. Isaac Newton described universal gravitation in the 17th century. Later, scientists developed increasingly precise theories of motion, matter, energy, and celestial dynamics. None of them needed to know about this distant world for those principles to apply. That is one of the remarkable features of science. A mathematical relationship discovered on Earth can describe an object billions of miles away, even when that object has never been visited. You can close your eyes tonight without changing anything beyond your awareness. Haumea will continue rotating. Its moons will continue orbiting. Light will continue crossing the immense distance between worlds. The solar system does not become less active when we stop watching. It simply continues. And perhaps that is a fitting place to rest with this world. Haumea does not need to be close for its physics to reach us. Its distant motion can be measured, its history can be reconstructed, and its existence can become part of what you understand about the universe. The equations remain the same. The distances remain enormous. Our lives remain brief. But within those brief lives, we can look outward and recognize patterns that have been unfolding for billions of years. Somewhere beyond Neptune, an egg-shaped world keeps turning through the darkness, carrying the evidence of an ancient collision, surrounded by fragments of its own past. You do not need to reach it to know that it exists. And as you drift toward sleep, Haumea keeps moving, exactly as physics allows. Long before we knew its name, Haumea was already turning. It was spinning before animals moved across Earth, before forests appeared, before continents settled into the shapes we recognize today. For billions of years, its rotation continued without interruption, carrying its elongated body through the distant solar system. Earth changed around us. Oceans formed, life emerged, species vanished, new ones appeared. Human beings eventually learned to raise their eyes toward the night sky and wonder what existed beyond the visible stars. Haumea kept turning. Centuries passed before telescopes revealed that the solar system extended far beyond the planets known to ancient observers. Even then, vast regions remained beyond direct knowledge, filled with objects too distant and faint for human eyes to distinguish. Haumea remained among them. Then, in the early years of the 21st century, astronomers began recognizing its presence through changes in reflected sunlight. Its brightness rose and fell as the rapidly rotating body presented different surfaces toward Earth. A distant world became measurable. Its shape emerged from those variations. Its unusual rotation became possible to determine. Later observations revealed companions, a ring, and surface properties that added new layers to the picture. Still, the world itself remained unreachable. We have never sent a spacecraft to Haumea. No human instrument has touched its surface, sampled its ice, or photographed its terrain from nearby. Everything we know arrives as information carried across billions of miles. Light leaves Haumea, crosses the outer solar system, and eventually reaches a detector built by people who may never have seen the world directly themselves. From that faint signal, we reconstruct an entire planetary system. The ring can be traced through changes in starlight. The moons reveal themselves through repeated gravitational motions. The rotation exposes variations across the surface, including a dark region whose nature remains uncertain. Even its most distinctive qualities are deductions, yet those deductions are grounded in measurements. That distinction matters. We are not looking at Haumea through a window. We are reading evidence and allowing physics to connect observations separated by immense distances. The result is incomplete, but it is remarkably detailed. And somewhere beyond Neptune, the actual world continues independently of our descriptions. Its rotation does not depend on telescopes. Its moons do not follow their paths because we calculated them. Its ring does not need our attention to remain in orbit. Haumea simply continues. While generations rise and disappear, its motions unfold according to the same physical laws that shaped it long ago. Our knowledge arrived only recently. Its existence did not. That may be the simplest way to understand what we have witnessed here. We did not create a story around Haumea. We slowly learned how to read a story written by nature billions of years ago. Tonight, you are part of that reading. A distant world is turning, and for a brief moment, we are here to notice.